My name is Vasu and I'm pursuing my master's in UIC. So I took one of the subjects which is cloud computing, and as part of that subject, there's a project that I'm currently working on. This project is mainly concentrated around distributed computing on cloud, and one of the framework that we use extensively here is MapReduce. So this project is all about that, and so I'll start off with the project and its description. So as you can see, it's Hadoop MapReduce on AWS EMR. I'll try to cover all the components that are involved as part of this assignment. So let's start. Right, so the content for this PPT is we basically cover the project overview, the problem statement, the proposed solution and implementation of that solution, and also the future scope of this project. Right, so starting with the project overview, so we were given an assignment by a professor, which involved uh, creating a solution of comparing two different graphs without using any of their node IDs, and you just had to take in the account the properties of the nodes and edges. Now, in order to do that, you had to compare each node with every other node in the other graph, and which is very compute intensive, and hence the solution we are implementing here is MapReduce. So MapReduce is a cloud distributed framework where you have the input, which might be a large file divided into small subsets, and those subsets are then given to each compute node, which is called a mapper. And each mapper performs certain kind of task on those input sets, and then gives it out to another node, which is called a reducer, which combines the output, and we can then have a consolidated output where we can make decisions and calculate results on our performance. Right. So um, the goal of the project was about comparing these graph edges and nodes. So these graphs and edges have certain kind of properties mapped to it, which we had to take into account. If those properties were modified, we took that as a modified node. If those properties were not there or the node itself was not there, we took the node as removed, edges as removed. And similarly, if the new node was added or edges were added, we compared the properties, saw that a new node has been added, which is not there in the original graph, and we add that in our result. So now there can be multiple nodes, multiple edges within a single graph, and it becomes difficult to uh, have a solution where you map the nodes with the other nodes without using this MapReduce. And therefore, I will discuss about the implementation. Um, so we used the Hadoop framework for MapReduce and also some other libraries that I will talk about shortly. So moving on. So the proposed solution was, as I already discussed, is the MapReduce framework. And in order to divide our graph into smaller subsets, we use induced subgraphs as a method. So what is an induced subgraph? When you have a graph and you want to cut it into smaller chunks, what you can do is follow an way of inducing the subgraphs, which basically performs or runs on top of having a list of nodes that is given to those induced subgraphs, and it will automatically generate the edges that are already there in the original subgraph. So it will inherit those edges and give us a subgraph which has both the edges and the nodes. So once you have those induced subgraphs, you can input these subgraphs into the computing nodes and start your computation or just calculate your similarity score. Right. So how was this implemented? For creating those induced subgraphs, we used a library which is provided by Google Guava, and it follows the same principle wherein you give the original graph, you give the set of nodes, and it will generate the induced graph on top of those nodes. Now, the enhancement that was made as part of this solution was that we first traversed the graphs using a binary first search method and generated those adjacent nodes so that we have meaningful graphs, not disjoint graphs or subgraphs. When you simply have the input being given as nodes, it can easily lead to having disjoint nodes which are not related to each other. So you might lose on edges. So we made sure that we traverse through a binary first search approach so that we don't lose edges and we have meaningful subgraphs. Now these subgraphs were, as I talked about, sent to a mapper. A mapper is again a part of that Hadoop MapReduce framework where it performs operations and generates a key value pair, which is further taken into account by the reducer. So once this mapper and reducer framework was done and implemented locally using Hadoop, we moved the project to migrated the project to AWS EMR, where you had you had AWS being used, and services like S3 and EMR were essentially used to run this project. Right. So I'll move on to the demo part now. So I'll first start with the AWS EMR because sometimes the computation takes time. So I'll start with the AWS EMR on how I've deployed that. So I'll go to my AWS console and open the buckets, S3 buckets. So right now I already have a bucket which has my jar file. In order to create your own jar file, so since this is the project, like I use this project called Netkin Sim to compile my code. I just ran spt compile assembly to generate the jar file. So once the jar file is generated, you can upload it to S3 in this folder, and uh, and you will then further use this jar file to put this as an input to the map in EMR, AWS EMR. Yeah, so this is the jar file that was imported. It's in this directory, and the input has uh, three files right now. The first is the netgraph original file, which is serialized and contains the original node. Second is the netgraph perturbed, which is the modified graph, again serialized. And then you have the YML. So this is the ground truth. Like it has the mappings of which nodes were changed and which edges were added, and all that information is there. However, we can't use this YML, and also this YML was used taking into account the node IDs and the edge IDs. And since we can't use that, because in real life scenario, you might have cases where you are not given any node ID. You just need to map or compare the nodes with their properties. Right? So coming back to the edges compare directory, we then have shards. Shards, as I talked about, are the input values given to the mappers. We have edges shards.txt and node shards.txt. Now these shards are generated by my program, which I'll cover later on. And these shards are basically nothing but a text file where you have the edges mapped with the are added with the edges of the perturbed or the modified graph. So a single shard will have one set of edges for perturbed and one set of edges for original. And sequentially or iteratively, you will map each of the original edge to the other perturbed one. So this is similarly, you have the file for nodes as well, which is called nodes shards.txt. Now, these files are given to the MapReduce function, and they perform the calculation on top of it. Now you have the output file. So right now it's empty. So this will be loaded or run when the MapReduce completes. So once the MapReduce completes, these files will have the intermediate results as well as the final output of the MapReduce. Right. So talking about running an EMR cluster. So let's start with that. I'll uh, start from scratch where I will go and create a new cluster. So I'll click on create cluster and click on my cluster. You can name it anything. I'll name it graph comparison. And it will run on the latest EMR version. So I just need the Hadoop to be there. I can check all the other files and run on instance, not EC2 fleets. Change the instance type to M4, M4.x large or large. You can choose anything depending on your requirement or the computation requirement. For everything, I'll just add M4.large. So these are EC2 instances which will be run as a cluster, and the instance type I'm giving to them is M4.large. Right. So right now I'm just using one core and a task as part of this cluster. And going further down, you can see there's automatically an S3 location where your output of the MapReduce will be stored. These are the logs. Like since MapReduce have multiple components, you can see those logs for those components under this location. So now one thing that we need to select is the IAM role. I'll choose a service role that I already created in my deployment, which is the EC2 EMR IAM role. So I'll just use that. Also, I'll show you what are the permissions given to this IAM role. I go to IAM. You can go to roles. So this is a newly created role called EC2 EMR, and these are the permissions that are given to this file or the role. So now coming back to creating a cluster, since we have chosen all the necessary parameters, we can go ahead and create the cluster. But before that, we must need jar file or our program to be added to this cluster. So we start with naming the jar file and we'll call it netgameslim and the jar file location. So I'll go to S3 and check for my file path, which is here, and just copy the S3 URI in the cluster. Right now, I don't have any parameters because all of my parameters are covered as part of the program that I'll show just in a few minutes. So let's save the step and create the cluster. So now the cluster will be running, and you can see that the cluster has started. It might take some time because there are multiple nodes right now. So this competition is happening on 300 nodes. So it might take some time to complete. So meanwhile it completes, I'll quickly go through the project. But before that, let me just make sure that my output file is empty, which is the case. So I'll go to my program now. Right, so this is the NetGameSlim project. I'll cover the part wherein we compare those graphs, the original and the put out one. So I'll start with the main, source main, which contains all the files, your resources, your input, output, and the test cases as well. So this is source main directory. I'll go to Scala. So I have a bunch of helpers and graph utils functions. So I'll start with main. So the control of uh, this netgame slim will first go to this main file. So let's start with what we are doing right now. So now once the main is executed, it first goes to the graph builder or a load graph call, which basically takes the output or the original graph or this perturbed graph file path and loads it into the program. So once this graph is loaded, we can then further uh, form multiple calculations and permutations on top of those graphs. So this is just a function to load both the original and perturbed graph. Then you move on and have the subgraphs created. Subgraph is a different helper function which is in graph utils, which is subgraph generator. So I'll see what we have in the input section. So we have, this is the important part, where you have mutable value graphs and graphs imported from the Guava library. So this mutable value graph is the one which we use to create those subgraphs. So what we do is just do a breadth first search, which is this algorithm, and traverse through the node and generate a list of induced subgraphs, which is then behaving as a shard for your MapReduce. So this is done for both perturbed and original. And once those induced subgraphs and are generated, we move on to the main function again and see that we actually write these uh, subgraphs into a file. So in this program, what I have done is have two files, one for nodes and the other one for edges, um, and MapReduce and different MapReduce performs on those two files. So these are generated in that I showed as well for both edges and nodes. We have a list of actions, list of nodes for both perturbed and original. Now, once you have those shards ready, you need to start your MapReduce on top of it. So that is called by our job scheduler. The job scheduler is another module or class which we use as part of this project, which schedules your MapReduce task. So I'll go over this extensively. So the import function contains a bunch of Apache Hadoop imports, and this is necessary for running your MapReduce. So all these configuration files that we set for the Hadoop configuration are done through this, right? And so once these files are imported, we need to set the configurations. So these are the configuration parameters. So as you can see, we set the job mapper class, we set the reducer class, we set the input path and the output path. Input path will be the shards and the output path will be the output that the reducer will write into. Right. Similarly, so we have these jobs for both nodes and the edges. So coming back to map, the main function again. So now since you have those mappers and uh, reduce functions ready, I'll quickly go through the output of them, right? So I already have some pre-built files that I ran earlier for these output. So I'll start with the H1. So if I compare the the intermediate output, so it will be like this. So here you can see that there is uh, a list or a key which is mapped to a set of lists or dictionaries, as you call it. So here 0 to 20 is of, so on the left column rather is of original graph, and the right hand side contains the keys and the values. Value is the similarity score. The keys are for the perturbed graph. So basically, what does this signify? Like the original graph will 0 to 20 is basically the start node and the to node. So the edge between node 0 and node 20 is mapped, and the score is calculated with the edge of 37 to 82. Again, these are for perturb, and all of these are calculated for each of the perturb graph edge. So once you have those score values, it's just a matter of performing some calculations on top of it to generate the exact match. So this is the intermediate file. Now there is a second MapReduce which runs on the edges itself, the output of this file, and it generates a final edge output, which is something like this. So this is the key matched perturb, min score perturb, and removed. And as the name suggests, the matched basically gives you a set of edges which are belonging to the original graph. These are matched of perturbed, and these are the perturbed edges which have the minimum score. So these two were calculated in order to have the value of the added nodes in the perturbed graph. So if you just subtract matched perturbed or min from the min score, you will get the added nodes in the perturbed graph. So, and removed is the list of edges which were removed from the original graph. Right. So since I talked about the YML file, so let's look at that as well. This is our source of truth. So the file we saw earlier was our assumption, or was created by a logic that we implemented, and this is the function. This is the file where we can compare our results to. So the next part of the program is about that, where we compare our results with the YML file. So in order to do that, we pass the YML file. We pass the file generated by the reducer, and we then compute the results. So there are a bunch of formulas in the results that are used. I'll link those, like also I'll have those links added in the description about induced subgraphs and this netgame sim GitHub repository, so that you can see what all formulas and libraries were used. Right? So the last concept that I wanted to touch base was about the similarity score that is calculated. So that is calculated as part of the mapper function, and I'll go to the mapper function. I'll open this. So I have two map functions, MapReduce functions, one for nodes and one for edges. Both are quite similar, and I'll just explain about the nodes function. And here you can see that there's a function called calculate node similarity. Right. So now this function is basically the one that we use for the comparing the nodes and the edges, and it's very simple function right now, wherein we have a set of nodes from the original graph, which has the properties of the node added as a set, and we have the set for the perturbed graph. Now, in order to calculate the score, what we use is a Jacobian methodology or Jacobian index, wherein you calculate the intersection size. So every property that is matching will be part of this intersection size, and you calculate the union size. Then you perform the division of these inputs, and then you calculate the score. Now, further enhancement to this is calculating this score by having some weights assigned to these properties. There can be a case where one property is important in order to judge whether the node is similar or not than the other. So in order to incorporate that, we have weights added to these properties, which improves our accuracy. Right. So this was about the similarity calculation, and that pretty much covers the project as well. So I'll go back to my MapReduce task, right? And see if that is completed or not. Yeah. Right, so right now it's still running. It's still in pending state. So meanwhile it completes, I'll go back and uh, to the PPT and see cover the last slide. So the future enhancement for this project is to test the different algorithms. So right now we are using the Jakarta index to calculate the similarity score. We have multiple algorithms. I've worked on SimRank and other machine learning algorithms which are in progress, and to just to improve the accuracy and the performance of this program. Second one is about expanding this project to the other graphs. So right now it's restricted to the net graph uh, or the mutable value graph generated from Scala. Sorry, from the Guava library, but I want to expand it to cover all and each graph that they might be. Right. So yeah, that was it from the PPT. I'll just pause for a moment. Meanwhile, my MapReduce completes. Right. So as you can see, my MapReduce is now completed, and here you can see the result. It's showing 1 against the completed section, and let's see what does the output show. That's the good part is like I don't have any standard errors encountered as part of the program. I'll quickly go over the syslog, which is important. So going on over the log file, you can see for the first one is to actually loading the net graph of both perturbed and original. So once the original and perturbed graph are downloaded, you can further or loaded into the program. You can further do the computation. Now you have the shards created under this file, and your MapReduce starts. So all these log files are generated from the MapReduce. Right now, it will generate these 4 output for the MapReduce. And once the MapReduce is done, you will have the output stored in S3 as well. So the last part, I'll cover the output of the S3. And once the S3 files are stored, you can see that we take those S3 files and calculate the scores. So this is the score. We have, we called a match between the 2 nodes as a traceability link or 2 edges as a traceability link, and they might be a bad traceability link and a good traceability link. So these definitions are there in the GitHub link that I will provide. And so according to these definitions, we calculate and increment the CTL, the bad traceability link, and calculate the eventual score. Right. So here you get the precision and the value. So this is completed. The program is completed. We have all the log files as well. So going back to the output file where the MapReduce intermediate files are stored. So this is this is what it looks like. You have the job edges. So again, this is the intermediate file. You have part 000. So MapReduce follows the standard, which has the out of the reducer. So I'll open this file again. As I said earlier, like this is similar to what we saw earlier about having a left-hand side column mapped to a original graph, and the right-hand side is basically key value and the score, or mapped to the bottom graph. Right. So let's see the job edges final one, which is more interesting to view. So these computations were done on a set of 300 nodes. So we'll have multiple sections. So let's download this file. So as you can see, you have the matched nodes, you have the min score, you have the removed edges. So let's quickly go over the, the files for the nodes as well and see what is there in the final result. So yeah, here you can see you have a bunch of nodes being matched. You have the min score being predicted, and also the removed nodes. All are part of this uh, file. Yeah. Okay. So right. So that was all from the EMR part as well, and hopefully you got an idea about the MapReduce EMR and about the graph computation. And I'll place all the relevant links to MapReduce and Hadoop and as well as EMR in this video description. Thank you for watching.